solve the consensus problem in all realistic networks that we could think of, despite the FLP impossibility result. And that spawned another 10 years of like frenzied consensus research, which slowed down until just a few years ago. And there was another huge theoretical discovery in consensus that I feel like I should share with you very quickly. This was work of a graduate student at Cambridge named Heidi Howard, who was working with Dale and Malky. It's called flexible taxons.
It was 1985.
85 was FLP, thank you. And then like Taxos was like 94, 95. So it's like 10 years went by where people were like, forget it, there's no point, it's impossible. And then people were like, actually, it's extremely likely, despite being impossible. Okay, so how do I approach this? Remember that the prepare phase requires a majority of replies. Okay? We need to hear back from the majority of acceptors to consider that we've successfully prepared something and go ahead and get it accepted. Right? And the accept phase, similarly, requires replies from the majority of acceptors. Only when we get replies from the majority of acceptors who all parrot back, our round that we're doing now, the thing is accepted. Why? Why do these two things require the majority? What property of majorities are we relying on there? Yeah.
You're looking for there being a node in the intersection between any two majorities.
At least one node is going to be in the intersection. And what that means is that if Alice has somehow gotten, so we want accept quorums to intersect, because if Alice has somehow gotten a bunch of people to accept x equals 1, we want somebody else who comes along. Oh no, so this is an accept quorum. We want somebody who tries to prepare a new thing, they have to know about x equals 1, because x equals 1 might have been chosen, right? So we need to make sure that every new prepare majority intersects with every accept majority. We also want every accept majority to intersect with every accept majority and every prepare majority, right? Or do we? So what Heidi realized, and it's kind of amazing that it took people so long to do it, especially considering how many smart kids have been staring at this friggin' algorithm for how many decades, right? What she noticed was, this is way over-constrained. Because the property that we really need to ensure agreement is only that every prepare majority intersects with every accept majority. Now, put on your quorum replication N, R, and W hats for a minute, and think about what this says about the design space. Right? So if there's 5 acceptors, I could have a world in which I only required my prepare phase to involve one of those acceptors, provided that my accept phase used 5, so that it intersects on just 1. I could do the opposite. I could say every prepare phase needs all 5, accept only needs 1. I could do 3 and 2, I could do 3 and 3, no, I can't do 3 and 2. I could do 3 and 3, I could do 4 and 2, right? There's all these different ways that I can negotiate this. It doesn't need to be a majority, it's just that the two need to intersect. In much the same way that, we saw that R plus W had to be greater than N in order that every read and write quorum intersected. Anybody have any thoughts about what you could do with this? If not, that's okay, because this result came out 3 years ago, and the systems community still hasn't figured out what the fuck to do with this yet, but there's a lot of excitement. What do you think you could do with it? Does anybody care? Do you care? Yeah.
So I haven't followed any super recent work, but when I talked to her back in 2015, the reason she was kind of investigating this in the first place was because she was interested in heterogeneous networks of, say, maybe you have a data center machine, but then you also have a phone, and you also have some IoT device, and you might not necessarily want to have the same. Paxos treats all of them the same. Right? And in this setting where you have all these heterogeneous devices, maybe you don't want to treat them the same.
That's absolutely right. This is the main research area of our colleague Faisal, who just joined too. So if you're interested in flexible Paxos at the edge, thinking about data centers cooperating with mobile devices, cooperating with trailers with mini data centers in them, that's kind of Faisal's area as well. yeah, I think she was interested both in device heterogeneity and also in decomposition of the protocol, right? Trying to figure out, can we move, and this is a bunch of work I did in my PhD too, like at some level, all consensus systems involve sequencing and dissemination and application. And you can imagine not everybody doing all the roles and moving roles around that. Some of her early work was doing that too. So anyway, one thought that I have, one obvious thought, is the trade-off stuff, like when we looked at quorums, right? Which is like, what if you think that you have a super stable proposer? You've got a really good leader election protocol. You think that that proposer is just going to be alive for years. Then it might make sense to say, I'm going to make my prepare quorum all 5, and my accept quorum just 1. That way, it couldn't be faster or more available to do accepts. And in the unlikely event that we need to reboot and start again, now we pay a substantial cost. Now this wouldn't be ideal because this is not fault tolerant. This means you can never restart without a reconfig. So you probably would want to say like 4 and 2. But you could say, like, in a world in which I think the proposers are stable, I can tune my quorum sizes to exploit that, to make the fast path super fast. Or on the flip side, right? If I'm doing Paxos across a bunch of IoT devices that have low battery power or whatever, I think that they're frequently going to go offline, and leader elections are going to be the common case. And so maybe I actually want to say, yeah, you know what, 4's fine. I just want it to be like super quick to get going again. And so I don't know, use your imagination. That's like an obvious gloss on it. But I think what's interesting about this is that, you know, for 20 years, we thought it had to be this way. This is the way I taught it. Like, it didn't have to be that way at all. Now, it's more complicated to teach it the other way. That's why I still taught it. But it's, you know, sometimes you're the 1,000th person to stare at an algorithm, and it's just like, you gotta figure it out. All right. Okay. Let us never talk about consensus again. Cool. All right, so, you know, we got like 20 minutes.
The way to do a talk review. Quick start. Just quick start.
Let's start by defining the notion of consistency that we've been using all along for strongly consistent systems, like a little bit more rigorously. And I mean a little bit, because I'm just going to draw a picture. But it's more rigorous than what we've been saying, right? So let's imagine, and we haven't talked about this before, but let's imagine that I have some kind of description. I'm going to call it a specification, D. And it's a specification of the expected behavior of Doris, the single-site database. And it describes all of the executions that Doris could get into. Now remember from before that just because Doris is a single-site database, it doesn't mean that for a given set of inputs she only produces one output. There could still be non-determinism in the communication of the clients with her. Right? So for example, I might have a client 1 and a client 2, and they both send a thing. Client 2 says foo, and client 1 says bar. And all Doris does is count to 5 and then output the first thing she saw. Well, obviously there's 2 executions of this system, right? There's the execution where she saw foo first and the execution where she saw bar first. So this is just to say, even given a sequential specification of a program running on one computer, that program might give rise to more than one execution with more than one output. So we might talk about, so this is a specification called D, and we can talk about the runs of D, giving rise to some space. And remember, the way I like to visualize runs is there's this big space, and the dots in the space represent the actual execution of the protocol. It might have different Lamport diagrams, right? Say, these might be the runs of this protocol. And then I delineate them by saying, this is D. You know, D is a circle identifying some runs, subject to some input, but let's assume that the input is like fixed, right? Why is there more than one dot? Well, because we could have had this execution, you know, and we could have had this execution, right? Those are different dots. Same D. She just outputs the first thing she saw. You with me? But let's imagine now that D is not some toy that outputs the first thing she says. it's the API for the database, right? So you can, what can you do to D? You can send it reads and writes. If you send it to write, it remembers what you told it to write. If you send it to read, it returns the last write to the variable requested, right? Okay, that runs the D. Now let's imagine that I have this other spec. This is what you might call a sequential specification in the sense that it's supposed to run on one computer. There's not supposed to be any non-determinism. It's just supposed to be straight line code. Okay? And we might also have a spec of a distributed database. In this case, let's let the spec P be a specification of primary backup. Now, like D, primary backup gives rise to some set of runs, some set of dots in this space, right? Okay. Remind me what we said it meant for P to be strongly consistent? Say again? That's exactly what I wanted you to say. P is strongly consistent colloquially if I can't tell it's not D. Right? So pictorially, what would P need to be strongly consistent?
It would need to be the circle D.
It would need to be exactly the circle D?
It would need to be the case that there were no runs contained within D that were not contained within P.
Good.
And
So strictly
potentially
speaking,
also runs
it needs to be inside, possibly identical too. Right? Because what we want to be able to say is, if the runs of P, if the runs of D are strictly contained in the runs of D, then P is what we've been calling strongly consistent. Right? Every one of the D's is a P. Sorry, every one of the P's is a D.
Yeah, what about also the...
Okay, that's like another.
Sorry.
Yeah, I was going to ask about...
Right? So usually the intuition is that we want it to be exactly the same circle, but definitionally it just needs to be inside the circle. And does everybody buy this? This is the same picture I was drawing when I was drawing broadcast protocols. The idea being the more restrictive specification is a smaller circle, precisely because it rules out more execution. Right? So in some sense, viewed in this way, here is a slightly more formal, less colloquial definition of what it means to be strongly consistent. You have to write down what it means to be Doris the database, and the space of runs that you can give rise to, what it means to be primary backup, and show that every execution of the one is equivalent to their execution. Right? Good? Cool. So, what does it mean for, I guess, okay, well, let me ask this first. Let's say that I had this specification Q. What can I say about Q with respect to D? How would I compare them to each other? What can I say about them?
Your picture implies that there are runs of Qs that are not the same as runs of D.
Which means what?
That there are instances of behavior where you can tell that Q is not D.
Yeah, exactly. So we would say that Q is strictly weaker than D, because D is contained in Q. All the dots that are in D are also in Q, but there's dots that are in Q that are not in D. Whatever Q is, it is a strictly weaker consistency model than the consistency models of P or D. Right? So sometimes to say that something's stronger, it's just to say contained in, and to say weaker, it's just to say contains. Yeah? Do we think that the containment will always be perfect, or do we think that there will sometimes be like consistency models or specifications that look like that?
It seems like there would be.
It seems like there would be, and so maybe this isn't the right way to visualize it. Maybe the right way to visualize it would be like some kind of lattice or something like that, right? Unfortunately, I don't have all the consistency models in cache at this time, so I might postpone the big lattice picture for later. But just like we had a lattice of delivery properties, where some delivery properties are strictly stronger than others and some are incomparable to each other, it's going to turn out that our consistency models form a similar lattice, where a great many of them are strictly bigger or smaller than others, and others are sort of orthogonal and hard to compare. Now, I think that when I do draw this lattice, I'm going to give you a little sneak peek of it. You imagine that there's a few things at the top that are very strong indeed, and then there's sort of families of related things. Okay? it's going to turn out that you can draw a bright dividing line or frontier across this lattice that's very meaningful with respect to this class. What do you think this line is dichotomizing?
Strong and weak consistency.
Okay, so you certainly could draw a line that delineated the things that at least colloquially we say are indistinguishable from single-site systems than other ones. Actually, you know what? You're right. So it is going to be that line, I guess, in some sense. Yeah, okay. What other thing from class is that corresponding to? Like, okay, if I go above the line, I get strong consistency. If I go below the line, what do I get? Because if the answer is nothing, I would always just go above the line. Availability. Right? So there's this sort of, this is the cap gap. Right? There's going to be like this bright line where you're like, there's going to be some consistency models down here which give me some properties I like. And there's going to be some consistency models up here that give me some properties I like. But it's going to be the case that these consistency models are not available under partition. And these consistency models are not consistent necessarily under partition. Right? So CAP gives us a way to sort of bifurcate or dichotomize the space of consistency models, which are hierarchical in nature, with a cut. Okay, that's one interesting thing. Here's a more interesting thing. And this is really, I don't think this has been proven. Maybe Lindsay, maybe you know better than me. But there's this piece of folk wisdom that there is one consistency model. I think I've already said this. But there's one consistency model that's sort of maximally close to the cap gap. There is a strongest available consistency model.
Eventual.
What do you think it is?
Causal. Eventual.
Causal consistency.
There you go.
Causal consistency is, and this is the part that I'm
Just
getting.
won the lottery.
How do you know that there doesn't exist another consistency model that is even closer to the line? I don't know. But Mark has definitely published on this. Causal is the strongest, strongest partition tolerant consistency model. Now, what do we mean by, this is a good opportunity to say, okay, so what do we mean by strongest? Well, what we would mean is we've drawn a bunch of circles in this space. And causal is the circle in this space that happens to be annotated with is available, and also circles the smallest number of dots, right? Because the strongest consistency model is the one that rules out the largest number of executions, right? So it's going to be all, let's imagine, okay, let's talk no more about strongly consistent models. Let's just draw weakly consistent ones in this picture. It's going to be the case that there's these different ways you can draw weakly consistent ones, but maybe there's one that circles the fewest dots, maybe. And allegedly, that's causal consistency. What do you think about that?
Okay, so how are we defining availability?
Oh, that's just some binary thing. Like the system either can immediately respond, in the CAP sense, in the Gilbert and Lynch sense. The system can immediately respond with a reasonable response under
How do you define reasonable?
I'm sorry, I can't help you right now. Like a in specification response.
Okay. But a response that violates causality would be considered unreasonable?
That's right.
Well, then you sort of begs the question, right? Like if you're explicitly ruling out things that violate causality as not being reasonable, then
Well, here's what I think the intuition is, but I think that we can find counterexample to it. And I think the class, some of the people in the class already have, right? Which is that what's the bad thing that can happen in a causally consistent system? The bad thing is like incomplete information flow, right? The idea is like I have these two things, X and Y, where X happened before Y, and stuff's being like asynchronously replicated, right? And we're afraid that Y can get over here and be read, but not X. And then that poor person who read Y goes back and tries to read X and can't read it and is confused because they saw an effect without a cause. And at some level, that is the canonical anomaly that we want to be ruling out in any causally consistent system, right? Incomplete information flow. And I think the intuition is, and then of course strong consistency says a lot of much stronger things. It says things about recency. It says you have to read the most recent write to a value. So strong consistency involves a clock, and this doesn't, right? So Now let's imagine a world in which Alice and Bob can't talk to each other. Well, first of all, there can't be incomplete information flow if there's no information flow, right? And this client can happily do reads and writes to this side of the partition and enjoy causal consistency on this side of the partition, and ditto this client on this one. So I think that's the intuition that makes them say, look, if there's a partition, first of all, obviously we're available. Because if I do something and I impose a cause and effect, obviously I can read both. And there's no way for some but not all, it's some kind of partial failure, right? And there's no way for some but not all of the information to flow. Okay, fine. But as students who are doing this assignment right now have noticed, if that's true, right? Well then, can't I do a situation where I'm like, x equals 1, and then I go, read x. And now we're back in cap country, right? Like, B has to either say, let's say the initial value is actually 0, B has to either say it's 0, or I don't know. And one would be inconsistent, the other would be unavailable, right? So I think that, like, I think that this statement that cap is the strongest available, blah, 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 is not very well, I think that the bottom line is cap doesn't make it. It doesn't type check very well. And it depends what you mean by availability, right? Like, this doesn't seem available to me. Right? Like, what does B say?
It's not just me.
Yeah. So, but I think that, like, they're assuming that there aren't these partial partitions. And I think they're also assuming, very understandably, do we have time? No, we don't have this. So there's this set of weak things that are all implied by causality, that are weaker than causality, called session guarantees. And one of the session guarantees is called read my rights. And it's like the simplest session guarantee. It says if I write 1, and I go read the thing, I better goddamn well read 1 or something later. And it turns out there's a trivial tool for it, because Clarissa here can just have a buffer in which she writes all her rights. And if somebody can't serve it up, she can read it from the buffer. So I think at some level, like, maybe the causality people also thought, I don't care about this scenario because it's so trivially easy to work out. But at some level, that's like an unsatisfying answer. And it's because availability, it's like a star, right? You like look at it and it's gone, you know, and you like look away and there it is again, you know. So I think like, and part of the problem is that, yeah, these terms are like used in a somewhat imprecise fashion. Okay, so we have 3-4 minutes left. Yeah.
So for the assignment, do we have B block and say I don't know? Or
Well, we won't set up this scenario because we think it sucks. So like, we won't, well, so here, let me answer that. I'll take 4 minutes for this. In the assignment, we ask you to return a payload for your reads and for your writes. We won't be using the payload that you return on writes to determine causal context. We're going to throw that causal payload on the ground. And the way that you interpret this, and what you're implementing is not exactly causal consistency, it's a large subset of causal consistency to make the assignment easier. The idea is that any write I do, the causal context will be determined by the last read. Okay? So in this scenario, there was no causal context. I did what's called a blind write in the database world. I send and prayed, and then I tried to read something. And the read had no causal context, so any return value would have been acceptable. So the right thing to do would have been to say, x is 0. And in fact, because we wouldn't even have passed the context, you wouldn't have known about this anomaly in the first place. You would have just gotten this read for x with no causal context, and you would have served it. So in some sense, like, you don't need to worry about the subtlety. We just won't put you in a position in which we're testing that. Yeah?
Even in that scenario, we can still generate something similar. You don't do that.
No. In that scenario, if I gave you the causal context, you would have to block in that scenario.
Okay.
Yeah. And I'm not asking you to do that. I'm not going to put you in a position where you do that. Yeah?
Don't writes also return a payload?
They do, but we're not doing anything with it. Like, that's the contract that I'm giving you, is that there are two things. I'm not going to care about the causal context that comes back on writes, and so that you, because imagine a scenario in which I do 2 different reads, R1 and R2, and they have like different causal contexts. And now I try to do a write. Which causal context should I use? It's an opaque field to me. That would be ambiguous. In a real implementation, I would know how to compare these 2 causal contexts, and I would choose the bigger one. However, I don't know how to compare your causal contexts. I have no, so this is something I said in office hours, but didn't say here. A causally consistent system, the client has to play along with the protocol. right? The client is responsible for proxying the causal context across calls. I do some reads, and then I do a write, and I have to tell the server that my write depended on those reads. If the client doesn't play ball, you don't have causal consistency. Unfortunately, the client participating in the protocol is very much at odds with what we're trying to do with this project, where we dictate nothing about how you implement the protocol. So I'm trying to say, I don't care if you do vector clocks, I don't care if you do matrix, cubed clocks, or pass around the explicit I don't give a rat's ass. But the problem is I don't know how to combine two of your causal contexts. So that you don't have to worry about that, I promise that these things will be lines, not trees. There will only be one last read that a write could do. Now, this change could be arbitrarily long, and somebody could read it, somebody else could write it, somebody could read it, it could be very long, but there's going to be no branching. So that you don't have to worry about, oh, what if I read a really new thing and a really old thing, and you guys propagated the old context, and then everything's wrong, right? You don't have to worry about that. Yes? Go on, please.